Hello to everyone and welcome to the class of natural gas engineering. In today's lecture, we will understand why natural gas properties estimation is important, how they are going to play important role in overall dealing with natural gas. So, if we go to our natural gas production system, we see the natural gas produces from the reservoir. It travels long distance from wellbore, bottom of wellbore to top, then it goes to separator and several process units, and then finally it gets transport to consumer. So, if I say the natural gas is a complex mixture of hydrocarbons with a minor amount of inorganic compound that depends on field, reservoir, particular well. So, a particular field may produce a natural gas with different compositions. The composition of natural gas vary from well to well, and from during the processing from one point to other point, the composition may vary. Not only the composition, the operating conditions like temperature, pressure also vary. As natural gas is not ideal gas, not a pure gas, it is a real gas, compressible gas, thus the properties changes. The composition of natural gas can be found. So, when the natural gas is being produced from a particular well, how to find out what are the composition of those natural gas? Are those hydrocarbon dominating, or which hydrocarbon is dominating the composition of natural gas, and what are the impurities, means inorganic gases, CO2, H2S, nitrogen and other traces amount are present in the natural gas. So, the analysis of the produced gas can be performed with the help of gas chromatography. So, in gas chromatography, we can inject the sample through the injector. With the help of a column, we can separate the different fraction of the gaseous mixture, and the detector, most probably it is a TCD, thermal conductivity detector, or the flame ionization detector for heavier hydrocarbon can be used. TCD allows us to detect the inorganic gases like H2S, CO2, if sulfur dioxide is present. So, the composition can be estimated with the help of the gas chromatography. Once the compositions are known, the properties can be estimated with the help of well established fundamental expression, correlations, chart and some empirical correlations. The estimation of these properties is very important. As I already mentioned, the gas which is not ideal gas, it is a real gas, changes its properties when it travels from one condition to other condition. Thus, the designing and analyzing natural gas production and processing as well as the transportation needs how the properties of natural gas are being changed. So, in the schematic when I had shown here, so this is the conditions where the natural gas is traveled from the reservoir to wellbore, then it travels all the way to from bottom of the wellbore to top. Choke device is here at the top, CPR. You will come to know these terms later on in the coming lectures. This is WPR, this is IPR. So, see here the pressure and temperature are different here. Again the conditions got changed here. The CPR, that says the condition of the pressure, or the point where the production is controlled, the pressure will be different, and because of the pressure change, the temperature changes. And then it goes to separator, where you are separating the gas, liquid and water. If the water and oil is present in the is being produced with the gas, and after the separator, it goes with series of the processing unit, where we are separating the water, or the water which could not be removed by the separator. We go to sweetening process, where we remove these acid gases like H2S and SO2, H2S, CO2 and SO2, and then it goes to remove of heavier hydrocarbons, because those heavier hydrocarbons are having more value than the methane. Those can be sold out separately to generate the money, like our LPG, that is having more energy than the methane. So, here we are having the dehydration system, sweetening system, removal of value added hydrocarbons, and then when it is ready to send to consumer, it is mostly the pure methane. So, see here when it was being produced, the unrefined natural gas has a variety of the composition, including hydrocarbon and non-hydrocarbon gases. Now, when it is ready to send to consumer, it is mostly the methane with trace amount of ethane and C2 and C3 gases. So, now the composition also getting changed. Thus, at each point when we are designing the equipment like separator, dehydration column, sweetening column, as well as the pipeline for the production side like the bell bore, choke conditions, everything, and similar on the transportation side, what size of the pipeline should be there, at what flow rate we can do. During the transportation, we installed some compression station, the compression duty required to compress the gas from one pressure to other pressure. All this depends on what type of the natural gas we are dealing, what are the composition of that natural gas, and what are the properties this natural gas is possessing. So, if we summarize the properties and composition of natural gas, I already mentioned composition varies. When the composition varies, the gas specific gravity also varies, pseudo-critical properties also changes with pressure and temperature, viscosity, which is very important property, also changes. Density, compressibility factor is another which shows the deviation of the natural gas from the ideal gas. Formation and expansion volume factor, heat of combustion, that determine the energy content the natural gas is containing, how much energy, because once we transport the natural gas to end consumer, it is being sold in terms of the energy it contains, and that is measured either in BTU or therm. Measurements, when we are measuring, when we are designing the measuring device, again the properties of natural gas will determine several coefficients, those are required to perform the measurement with the help of any meter or device. And when we are transporting this natural gas, the safety feature like the explosive properties, flash point, fire point, volatility, flammability also need to be known. And for the natural gas, the lower explosive limit is around 5% and maximum or upper explosive limit is 15%. It means when the natural gas in air, the concentration of natural gas in air is 5% or less than 5%, it won't burn, and when the concentration is more than 15%, again it won't burn. So, the flammability range is 5 to 15%, and all these are required. All these are required for the evaluation of the gas reservoir and gas well. What is the potential of gas reservoir, what is the potential of gas well, what is the total gas in place, and at what rate the gas can be produced. The production, prediction, future performance all depends on the estimation of these properties. You will see in the subsequent lectures how important these properties are, because these properties depend on the operating condition. That is why the complexity comes when we derive the analytical expression based on the fundamental understanding of the system. The equation those come out are very difficult to solve, and that is why knowing these properties as accurate as we can is very important to predict the performance of each and every process, as well as predicting the future of a gas reservoir. The processing, like I mentioned, separation and other processing unit. And for these safety features, the ASTM method can be used. Those are standard method to be used to understand the explosive property like flash point, fire point, but for the other properties we will try to understand the mathematical expression. Those allow us how to estimate all those things. And the natural gas production, when natural gas production started long back, the properties were estimated in the form of a very complex chart. For example, if the viscosity is measured, it is measured under different temperature and pressure condition in the laboratory, and the chart has been developed that account not only for the changes in the temperature, pressure, but different percent of the inorganic compounds in the natural gas. So, we will try to understand how those complex chart have been used to develop the mathematical expression. So, now what is the use of understanding all these properties? So, for example, as mentioned, natural gas is a real gas, it is not ideal gas. Even the density of a natural gas, that depends on the compressibility factor. So, compressibility factor should be known if you want to know the density of our gas, that is a mixture of several hydrocarbon non-hydrocarbon gases, depends on the constituent of the natural gas it is being made. Flow in pipe. So, when we are flowing the natural gas through the pipeline, either during the production time or during the transportation time, the compressibility and viscosity are two very important parameters. Those comes into picture, and both depends on temperature and pressures. If they are changing, the flow in the well or the behavior of the gas in the well or in the pipeline will also change. That's also I mentioned the pressure drop in pipelines. So, both in the well as well as in the pipeline, the behavior will be different. Again, temperature also changes in pipeline, and when the temperature is changing, the heat capacity value is required to understand how much is the heat loss is happening, and do we need, when we are changing the pressure, for example, at the choke device, when we change the pressure, suddenly because of the Joule-Thomson effect, the temperature goes down, and that determine how much energy is lost, and do we need to heat the gas to maintain the temperature, so it is not going to form the gas hydrate, and several other places the heat capacity is also required. You will see all these when you go in further lectures at a particular point, when we will be discussing about the well performance, when we will be discussing about choke performance, when we will be designing the separator and discussing the transportation of natural gas by pipelines. So, other properties like molecular weight, it needs relative density, specific gravity, or other way also the property can also be estimated in other ways, like performing the laboratory measurement. The Reynolds numbers need density and viscosity. Reynolds number is defined as rho V d by mu, but when we convert these things even in the quantity, those are known, still we need density and viscosity, and density can be converted with the help of some other known parameter in some other term, but still we need to know compressibility or viscosity to define the Reynolds number, which determines the flow under certain condition is in the laminar region or in a turbulent region. Not only to understand the flow regime, even to calculate several properties like friction factor, we need to know the Reynolds number value. So, that Reynolds number value depends on density and viscosity or in the flow rate. Thus, all these things need to be known, or the as much as information about the natural gas should be known to deal with all the process involved in the natural gas business. Properties of pure compounds. So, if we see, as already mentioned, the composition of the natural gas varies from hydrocarbon to non-hydrocarbon. In hydrocarbon, let us see they are in the range of this C1 to C7. They could be in the isoform or could be in a normal form also, but most of the natural gas are dominated by the methane and their subsequent percent of the other hydrocarbons C2, C3, 4, C5, C6, C7, and non-hydrocarbon gases N2, CO2 and H2S. They are the non-hydrocarbon gases. These are hydrocarbon gases. So, when we are dealing with this kind of the composition, those are the part of the natural gas, we need to know the properties of this compound to estimate the mixture properties, and the pure compounds property can be obtained or can be found in several reference books like Ahmed book of the reservoir engineering, even the economites data collection, or even in any thermodynamics book you can find out the properties of pure compound, like what is the properties of methane, what is its molecular weight, what is the critical temperature, what is the critical pressure. For all these compounds in the pure form can be found in the literature. And here I just gave an example of the composition of natural gas. Those composition mostly dominated by the methane. The natural gas means methane with other hydrocarbon gases and non-hydrocarbon gases, and the percent of this methane varies. Other compound percent just in very low compared to methane, and some percent of the inorganic gases. This is one of the example of the composition of natural gas, and this composition of the natural gas can be obtained with the help of gas chromatography or by other means also, which can tell us what are the compositions or the number of moles of individual component present in the mixture. So, with the help of knowing this information, what we can do, we can understand how the gas law will be applicable to natural gas. As mentioned, natural gas is not the ideal gas. So, P v is equal to nRT is not going to be applicable. If it is a pure gas like a methane, even up to certain point or at a low pressure, it may behave like an ideal gas, but at a very high pressure and having a mixture of different hydrocarbon, non-hydrocarbon gases, our natural gas follows the real law. And in real law, we are having this term where this Z compressibility factor is accounted for the deviation from the ideal behavior. So, the compressibility factor Z, that shows how much deviation our natural gas is having if it is assumed to be ideal gas. A natural gas mixture under reservoir condition is non-ideal. So, at a very high pressure, it is a completely non-ideal gas. And when we talk about reservoir condition, most of the time the information is transferred to some non-condition. Those are the standard condition, and the standard conditions are pressure means pressure value is 14.7 psi and temperature value is 520 degree. Those should be in the absolute term. So, the temperature either represented in the form of a degree ranking or degree Fahrenheit, either in the form of degree ranking or degree Kelvin, not in degree Celsius or degree Fahrenheit. These are the absolute value, and whenever you are having the data in other form, you have to convert into absolute value to apply to gas law. So, this compressibility becomes very important, because that compressibility says how much volume, especially the deviation in the form of volume, but the natural gas is having, or the natural gas which is under the investigation is having from the ideal gas law. And if we look in the literature, we try to find this deviation of the natural gas from the ideal gas. There are several charts are given long time back, and those charts are very complex in nature, because they are shown, for example, here just for the hydrocarbon gases. So, if it is assumed the percent of the non-hydrocarbon gases are in the trace amount or not present at all, we have to use this kind of the chart. And this chart says the compressibility factor can be determined if we know the pseudo reduced pressure and pseudo reduced temperature, that is here pseudo reduced temperature here. So, if we know pseudo reduced pressure here and pseudo reduced temperature here, we can use this chart to get the compressibility factor. So, let us see, this chart is divided in two parts. This is one separate, and in this way the reading of pseudo reduced pressure is from 1 to 8 here and from 7 to 15 here. So, the chart is same, upper side and lower side, it is just a representation of the pseudo reduced pressure on a extended scale. Here is up to 8 only, while here it is start from 7 to 15. And at a particular reduced temperature of a mixture, remember these are the pseudo reduced pressure or pseudo reduced temperature, means these are the mixture properties, that is why the pseudo word has been used. And the pseudo reduced means pressure divided by critical pressure or temperature divided by critical temperature. So, to know this chart or to read this chart, first we need to know what is the pseudo critical temperature and pseudo critical pressure values of the natural gas. So, if we know those things, with the help of this complex chart, we can read the compressibility factor. But again, this chart is only for the hydrocarbon gases. If we are having the non-hydrocarbon gases present in our sample or in our gas, we have to go to some other chart. This chart for the hydrocarbon gases is reported by Standing and Katz in 1942. They had done extensive laboratory investigation to develop this chart. For the non-hydrocarbon gases, if the non-hydrocarbon gases are present in the natural gas, the correction has to be applied for the natural gas compressibility factor, which is calculated assuming there is no non-hydrocarbon gases are present. So, if the gas gravity or specific gravity with respect to air of a natural gas is known, with the help of pseudo critical temperature and pseudo critical pressure, this chart can be read and the value of compressibility factor can be corrected for different inorganic gases like N2, CO2 and H2S. Each time we have to apply one correction factor to correct the value. Again, this is complex chart and this chart need specific gravity as well as pseudo-critical temperature and pseudo-critical pressure. So, when long time back when this chart were developed, there was no computational facility available to read this chart and develop some mathematical relation, but several researchers have put lot of effort to make very complex expression or the correlation, those can replace this chart and those correlation can be used directly in a mathematical framework to calculate the value of the properties like the compressibility factor in this case. Similarly, we will see for the viscosity also. Another for the inorganic gases, this Wishart and Aziz in 1972, they said for the inorganic gases only they had considered the CO2 and H2S. They said with the help of this chart you can estimate this epsilon 3 and this epsilon 3 can be used to correct the value of critical temperature and critical pressure. So, these are the corrected critical value of pressure for the mixture which accounts for the presence of inorganic gases, but only for CO2 and H2S. So, with the help of this chart, knowing the value of CO2 and H2S, again to read this chart we need to know the percent of CO2 and percent of H2S, then only this chart can be used to correct the values. What we corrected is T PC has been corrected to T prime alpha and this T prime PC this PPC has been corrected with the help of this T prime, I think this should be TPC, TPC and PPC, this has been converted to corrected value of critical pressure. Similarly, for the viscosity, if we are going to estimate the value of viscosity of the natural gas, again remember natural gas is a combination of several hydrocarbon and non-hydrocarbon gases, mostly dominated by the methane. Even in that case also, when the gas gravity is known and molecular weight is also known, with the help of this chart at a different temperature we can estimate the viscosity of the natural gas at 1 atmosphere. This is 1.0 means 1 atmosphere. 1 atmosphere we can calculate the viscosity of the natural gas. Later on that can be extended to high pressure, how the viscosity will change when the gas is exposed to a high pressure condition. But at 1 atmospheric condition, what is the value of viscosity at different temperature can be obtained with the help of this chart. This chart also suggests how to apply the correction factor for H2S, N2 and CO2. So, this chart is given for natural gas viscosity at 1 atmosphere by Carr et al. In 1954. They also developed another relation for elevated pressure conditions. They said once you are having the value of reduced pressure, reduced temperature and reduced pressure, you can calculate the viscosity ratio. That viscosity ratio is simply viscosity at elevated pressure divided by viscosity at 1 atmospheric condition. So, with this chart we can get the viscosity at 1 atmospheric pressure. With the help of this we can get the viscosity ratio. Knowing both the values we can calculate the viscosity at elevated pressure condition. Again reading these charts are very complex. So, before understanding how the mathematical correlations will be useful, let us understand how the simple properties those are required to read this chart can be estimated. This is very important because if you see this chart, the correlations have been developed from this chart only, and to read this chart we need to know how to calculate the molecular weight of a natural gas, we need to know what is the gravity of the natural gas, how to calculate the critical, pseudo critical temperature and pseudo critical pressure of the natural gas. All these chart are in the form of these parameter, and these will be again reflected in the mathematical expression or the correlation mathematical model developed to estimate compressibility factor and viscosity or any other properties, if that is a function of critical temperature, critical pressure, specific gravity, molecular weight. So, let us go one by one to understand these things. So, before going further, let us see one more properties again developed by Carr et al. For the viscosity of gases at 1 atmosphere. They said for a different pure gases, even the pure gases, the viscosity changes with temperature even at 1 atmospheric pressure, and the gas viscosity changes with temperature, and you can see viscosity increases with increase in temperature, and similar behavior viscosity increases with increase in pressure. We will come back to understand all these things. These are just to show why there is a need to calculate, to understand how to calculate the basic properties of the natural gas, just to understand viscosity, compressibility factor and some other parameter. We will revisit viscosity, compressibility factor later on. So, let us see, let us start with first property, that is the specific gravity. So, gas specific gravity is denoted by gamma g. This is the ratio of apparent molecular weight of a natural gas to that of air. So, it is simply in a mathematical term gamma g, that is gas specific gravity, is a ratio of apparent molecular weight of natural gas. Apparent molecular weight means we need to know the composition of the natural gas. Applying the mixing rule or the chain rule, we can estimate the apparent molecular weight of the natural gas. That will be in the numerator, and the denominator is the molecular weight of air. Either we can take a value 29, or we can calculate this with the approximation of assuming air is just composed of 79% nitrogen and 21% oxygen. Other gases are in the traces amount and not counted. With the help of that, if we calculate the molecular weight of air, that turns out as 28.97, that can be assumed approximately 29. So, the apparent molecular weight of the natural gas, as I mentioned, if we know the composition of each and every compound present in the natural gas, yi is the mole fraction. So, if we convert the information of the composition of natural gas in terms of mole fraction, multiply this with the respective molecular weight and do the summation for all compound present in the gas, we can get the apparent molecular weight. We will do a numerical calculation to understand this. So, I already mentioned yi is the mole fraction of component I, MWI is the molecular weight of compound I, NC is the total number of the compounds present. So, we have to do the summation for all the component present. For pure methane, if we calculate for a pure methane, the value of specific gravity gamma g will come out as 0.55. This is very simple calculation. Apparent molecular weight of pure methane is simply 16 or 16 point something, if we go with a more accuracy, divided by 29. If we do this, it will come out around 0.54 or 0.55. And for a rich or heavy gases, as the composition of the natural gas are dominated by higher percent of the, or by higher hydrocarbons like C2, C3, C4, the apparent molecular weight will increase in the same proportionality, and so the specific gravity of the natural gas. So, for heavy or rich gases, the value may reach up to 0.9 or even further. How to calculate yi? Either perform the gas chromatography, know the area, convert that area into mass percent. From mass percent, you can convert into mole percent or mole fraction. So, yi is Ni by N. Ni is the number of moles of component I divided by N, total number of moles total number of the moles of the natural gas. And with the knowing this yi, we can also calculate the partial pressure of component I in a mixture, just applying this Dalton's law. Okay. So, important point is knowing the composition. That says, even if you want to calculate any properties of a natural gas at atmospheric condition or STP, standard temperature and pressure conditions, we need to know the composition of the natural gas. If it is dominated by methane, 99% methane, then we can roughly calculate it, the properties, just assuming it is methane, or otherwise we need to know the composition. So, further, if we go further, pseudo critical properties of natural gas, as I already mentioned, these properties are called pseudo properties because these are the properties of a mixture, not of a pure compound. Critical, because the critical temperature and critical pressure are the pressure where gas and liquid can exist in the equilibrium. So, for pure compound, these are available, methane, ethane, propane, CO2, H2S, these are available in the literature. And for the mixture, if we know the mole fraction of each compound, as in the case of the molecular weight, if we know the value of yi, we can multiply this mole fraction with their respective critical pressure and critical temperature to get the value of critical pressure, pseudo critical pressure and pseudo critical temperature. Again, this called either the mixing rule, we can call it as a mixing rule or chain rule. So, for both the cases, similar expression can be applied to know the critical properties of a mixture, we call them pseudo critical properties of natural gas. So, let us take example, that example simple, it says if the compositions are given, calculate the apparent molecular weight, pseudo critical pressure and pseudo critical temperature of the gas. So, first thing should be known is gas composition. So, the gas composition, for example, we can identify with the help of any lab measurement technique like gas chromatography or something, and let us assume the same number I had put, that which I shown in earlier slide. C1 to C7 are the hydrocarbon gases with this percent dominated by methane, relatively dominated by methane is present, and N2, CO2 and H2S are also in the significant quantity, they are appearing in the analysis. So, we know the gas compositions. What is the next step? We can apply the mixing rule to calculate the apparent molecular weight, pseudo critical temperature, pseudo critical pressure, and once we know apparent molecular weight, we know we can also calculate the specific gravity. So, on the solution side, let us say we are having the compound, we know the composition or the mole fraction of those compounds present in the natural gas, and the summation of mole fractions should be 1. That is, I did here the summation and I say okay, the calculation done to calculate the mole fraction is correct, and from the literature, from the reference book or from other sources, I know the molecular weight, critical temperature, critical pressure of individual pure components present in natural gas. So, what is the next step? I can apply the mixing rule and calculate individual yi multiply by molecular weight. I can get the data. To get the apparent molecular weight, I just need to do the summation over this and I will get this value. Similar for critical pressure and critical temperature, I can calculate individual compounds fraction and do the summation over it. I can get the value of critical temperature and critical pressure of the mixture. So, simple calculation, and knowing the apparent molecular weight here, I can divide this with the molecular weight of the air, I can get the specific gravity of my natural gas. That is so simple calculation. And why I had shown this calculation? Because you may write one Excel program or a MATLAB program or any program where you can identify, where you can list down all the possible compounds, those could be present in the natural gas with their properties from the literature. And whenever you are given this set of data in terms of the composition of the natural gas, you just need to enter that, the calculation can be done automatically and you will get the parameters like the specific gravity, molecular weight, apparent molecular weight, specific gravity, critical temperature, critical pressure by just entering the data. Otherwise, every time if I change the next time the composition, I had taken another sample of the gas, and if the composition changes, for example, this changes to 0.81, and accordingly other composition will also get changed, because the summation of the mole fraction should be 1. And in that case, if it is done by hand or it is done not in a proper manner, you have to repeat the procedure again and again. And you will see when we will go further, all these are very important steps to reduce the workload in more complex system, when we need to understand more and more detail of more complex parameter involved. So, better from the beginning, from this first example itself, we are start writing our own Excel program or in a MATLAB program, and whenever the data are given, we can calculate. So, for example, here critical temperature and critical pressure, because you see any chart we had seen, if we are going to read those chart and composition got changed, if a natural gas of different composition given to us and we want to read those chart, again we have to calculate critical temperature and critical pressure. Thus, writing a program in the Excel or MS Office Excel is very important. Now, let us see how pseudo critical properties of natural gas can be estimated. If we know the composition of the natural gas, but there might be a possibility when the compositions are not known, but specific gravity was told to us. So, the data are given to us in the form of a specific gravity, not in terms of the composition, then how to calculate the critical pseudo critical properties of natural gas. So, a correlation for pseudo critical properties can be used, and these temperature and pressure can be determined from various chart or correlation developed in the past. And based on this chart, this correlation has been developed, and we can see if gamma c is given to us, that is a specific gravity, with the help of this set of the parameters. Those are very simple linear expression or linear relationship between pseudo critical properties and gamma z can be used to estimate the pseudo critical properties. Just we need to put the gamma z value, that is specific gravity, because it is known to us, we can get this value. But there might be a situation when these are not valid. Only these correlations only hold good when we are having the H2S is less than 3%, nitrogen less than 5%, and total content of inorganic compound is less than 7%, then only these correlations are good enough to use. But if the situation is not like this, the correlation with impurities correction for mixture pseudo critical properties has been proposed by Ahmed in 1989. Ahmed said include the composition of nitrogen, CO2 and H2S in the expression and use gamma g, because this properties is known to us. You can calculate the pseudo critical properties of the mixture, both pressure and temperature. But again, to use this expression for the correction of impurities, we need to know the composition of or the percent or the mole fraction of those impurities N2, CO2 and H2S, as well as the gamma g should be known to us. The mole fraction of CO2 or H2S are known to us. With the help of this chart, we can correct these pseudo critical properties. What we can do? We can calculate the pseudo critical properties with the help of this Goa and Galambur methods, and this is a very simplified methods, and these values TPC and PPC can be corrected for the inorganic gases, presence of the inorganic gases with the help of this epsilon 3. That epsilon 3 can be read from this chart, and we can get the correction, and this is proposed by Wichert and Aziz 1972. And further, this chart has been read in a mathematical sense, and it says if we know the percent of H2S and CO2, and let us say percent of mole fraction of H2S is B, and mole fraction summation of mole fraction of H2S and CO2 is A, we can put in this manner A and B and can get directly the epsilon 3 value. Instead of reading the chart, we can calculate with the help of this correlation, and this correlation has been developed from this chart only. So, using this we can go back and correct pseudo critical temperature and pseudo critical pressure value. several correlations have been developed. So, reading the chart developed when the computational facility were not developed, we were forced to use only the chart and read the chart with the information required to read those charts, like the critical temperature, critical pressure, gravity, specific gravity and the percent of the inorganic compound present. Later on, several researchers had put lot of effort to develop several correlations. Last slide I have shown 2 correlations. Here you can see the several correlations. This is the same Goa and Galambor correlation that we started discussing. This is a linear relationship between the critical properties and the specific gravity gamma g. Sutton in 1985 he had developed the correlation, and that correlation is a quadratic form of the gamma g to estimate the critical properties, pressure and temperature. But each model that has been developed or each correlation that has been developed based on the chart are having certain limitation, because a particular data set has been used to develop those such relationship, or they hold good only within certain limit of the other parameter, like what is the percent of the inorganic compound present, what is the specific gravity of the gas being handled. So, for example, let us go one by one. Sutton in 1985 he has that quadratic expression in form of gamma g, and this correlation is good when we are having the gamma g in the range of 0.57 to 1.68, and the gases are rich and the gas sample are rich in heptane plus with minor amount of CO2 N2 should be present, and there should not be any H2S present in the sample. So, if this conditions we are having the natural gas with this composition, with this condition, we can use this Sutton correlation to calculate the pseudo properties. And if nitrogen is less than 5%, H2S is less than 3% and total inorganic compound is less than 7%, we can always go with a Goa and Galambor, and this is the simplest form of calculating the pseudo properties. Standing in 1981, he had given similar expression as given by the Sutton, but in this case the coefficient got changed because the data has been used from the other source, and the correlation of the standing are good only without non-hydrocarbon gases. So, if the natural gas is not having is without non-hydrocarbon gases, standing expressions should be used instead of the other expression. Similarly, other expression in 2000 and 1989 by Ahmed, they also had given. So, both this is the quadratic form and these are suitable for gas condensate system. We are dealing mostly with the dry gas or the gas with a very small amount of the liquid present. So, mostly this correlation is only for the gas condensate system, or suitable for gas condensate system. It will give a more reliable value for the gas condensate system. Ahmed 1989 that we already discussed. If we are having the information about individual compound of inorganic gases, mostly the nitrogen, mostly the CO2 and H2S, we can use Ahmed expression to calculate, and this is applicable for mixture with impurities such as nitrogen, CO2 and H2S should be present in the sample. I think this should be N2, sorry for this should be N2. So, the Ahmed 1989 expression is good when N2, CO2 and H2S are present as the impurities, and knowing the percent of N2, CO2 and H2S, we can calculate pseudo properties. This should be N2. So, other correlation are in the form of pseudo reduced pressure or pseudo reduced temperature. We can get this value of natural gas mixture just at what pressure the natural gas is divided by the pseudo critical properties of natural gas. Similarly, can be done for the temperature. So, knowing the pseudo critical value, we can calculate the pseudo reduced value both for temperature as well as pressure, and they are important because some correlations are given in the form of pseudo reduced conditions. So, let us see in summary what we learned today. The specific gravity of the gas, that is simple, molecular weight, apparent molecular weight divided by the molecular weight of air, Apparent molecular weight can be calculated if the mole fraction of individual component are known. Gas critical properties like pseudo critical properties like pressure as well as temperature can be known with the help of known composition of the gas or the mole fraction of the gas. If gamma g is given to us instead of the composition, we can still calculate the critical properties, depends on the other information available or known to us, we can calculate this, and after knowing the critical properties we can also calculate the pseudo reduced pressure and temperature of the natural gas. With this I would like to end the lecture here, and in the next lecture we will understand how to estimate the viscosity, compressibility factor and some other important properties of the natural gas. Those are important in designing, processing and transporting natural gas. Thank you very much for listening to the lecture. Thank you.